100 seconds after the Big Bang, the universe is still expanding, getting less dense and cooler, and it enters a temperature and density regime that is similar to the center of a star. So basically the entire universe was a giant star at this point. And nuclear fusion began. And for about 20 minutes, nuclear fusion was able to continue. And although that doesn't sound like a long time, nuclear fusion was occurring at an extremely fast rate because the universe was so dense. And so the protons, which made up most of the universe, fused to make helium, just like it does in the sun, a tiny bit of deuterium, and a tiny bit of lithium. And predictions are that 75% of the current universe should be protons, 25% helium, a millionth of a percent lithium, and 0.01% deuterium, and that's what we see. In this plot here on the right, there are predictions for how much lithium and deuterium, helium, and hydrogen you should have for different densities of the universe. So you can calculate this for all sorts of universes of all different densities. Our universe is the little gray bar. That was the density of our universe. And so that's how you get those predictions, which we can then go out and test and find that indeed the universe makes this. 20 minutes after the Big Bang, the universe thinned out enough and cooled off enough that nuclear fusion stopped. And throughout this entire nuclear fusion episode of the universe, for these 17 minutes, although a lot of nuclear fusion was happening of hydrogen into helium, things were already too cool and densities too low for heavier elements. So we didn't get any carbon or oxygen or anything heavier than that. All of those elements have been made since. Just hydrogen and helium were made during the Big Bang, plus lithium. Once nuclear fusion stopped, and for the next 380,000 years, give or take a few tens of thousands of years, the universe was too hot for protons and electrons to combine and make atoms. So you had atomic nuclei, the protons and the few helium nuclei floating around, and you had electrons floating around, but they were never combined together. Now, when you have charged particles like protons or like electrons that are not bound together, photons can push them around. And so for this 380,000 years, photons dominated the universe, pushing around all these charged particles. However, dark matter, which we've ignored up till now because we don't really know where it comes from yet or what exactly it is, but if we put dark matter into the universe at this point, it does not interact with photons. That's why it's dark. So gravity can begin to allow dark matter to start to clump. Meanwhile, the regular matters get pushed around by the photons, and if you start pushing regular matter around, you will make waves, just like the ocean naturally has waves. And in the early universe, these would have been pressure waves, or what we call sound. So things were dense enough for sound waves to form at this point. And the way that sound waves work is that some areas of air or gas get compressed a little bit, and so they heat up, and then they push themselves outwards and do what we call rarefication. They become thinner and cool off, and then that process repeats. It's kind of like a giant slinky going back and forth. So sound waves were traveling through this early universe, and in regions where things were compressed, they got hotter, and where they were rarefied, they were slightly cooler. And then you had the dark matter clumping as well, so that tended to concentrate the waves in some areas around the dark matter. And this is beginning to make the seeds for what eventually became galaxies. But at this point, you basically had dark matter starting to clump and regular matter spread almost perfectly evenly everywhere, with these waves going through a little concentrated towards the middle of the dark matter. At this point, 380,000 years, the universe cools below 3,000 degrees. And once you get hydrogen and helium below that temperature, the electrons will combine with the atomic nuclei to make atoms. Once they make atoms, the photons don't interact anymore unless they're of exactly the right wavelength, so the universe becomes completely transparent to almost all wavelengths of light. Also, when this happens, you release additional photons, because remember, when an electron falls into an atom and goes down in energy levels, it's going to release light. And those photons have been coming ever since. Now, at the time, they were photons that would have been a black body with a temperature of about 3,000 degrees. But because expansion of the universe stretches everything, including wavelengths, these photons get stretched to longer wavelengths, which would make a black body temperature at 2.72548 Kelvin, which is what we measure today as the cosmic microwave background. So this hiss that Penzias and Wilson saw in their microwave detector that they thought might have been pigeon dew was really leftover photons from 380,000 years after the Big Bang, a time when the universe became transparent. When this recombination, as we call it, happened and the electrons and protons joined up to make atoms, then there were still some parts of the universe that were slightly denser than others. We had dark matter halos starting to form under gravity. Not very big yet, but they were starting to be there. We had sound waves of all different sizes, from very small wavelengths like we have in sound around us to wavelengths the size of current galaxies. Those all would have been around. The slightly denser areas, whether it was a sound wave or a dark matter halo or both, they'd be slightly hotter than the areas where it was less dense. Because of that, that imprint gets frozen in the blackbody spectrum that comes to today. And we see that imprint on the cosmic microwave background. Here's a picture of the cosmic microwave background once we've taken out our own galaxy, which also makes microwaves. And you see some red spots and blue spots. The red spots show places that are slightly hotter than the blue spots, and it's only by a tiny fraction of a degree, 2/10,000ths of a degree. But yet those slight differences, slight enough to change the temperature by 2/10,000ths of a degree, are enough that these slightly denser areas had more gravity and eventually became galaxies and stars. The cooler areas were less dense, and they became the spaces between galaxies and stars, what we call voids. So when you look back here, you see the universe as it was 300,000 years after the Big Bang, with slightly dense areas, slightly less dense areas, but overall mostly very smooth. After recombination, gravity's still around, so gravity's pulling stuff in, but there are no sources of light. Light can stream freely through the universe, but no stars have formed yet, no galaxies have formed yet, no black holes have formed yet, and so there's no new source of light, so we often call this the Dark Ages. Gravity continues to pull matter inward. It pulls in dark matter, it pulls in ordinary matter, but yet the universe is still too hot for stars to form. To make a star, you need a dark nebula. To get a dark nebula, you need temperatures that are starting to get close to absolute zero, no more than a few hundred degrees Kelvin. Universe at this point is 1,000 degrees Kelvin, can't make a star. But after 250 million years, so 250 million years after the Big Bang, finally the universe is cool enough that stars begin to form. And at this point the Dark Ages end, light from stars begins to come through the universe, and we are able to study that from the Earth. So we look back with our biggest telescopes today, we are seeing galaxies and stars that are near this limit of 250 million years after the Big Bang. We will see a computer simulation of this in the next mini lecture. So here's a summary of what we've talked about, the history of the universe, and I'll emphasize here what's important. We have the Big Bang. Not sure what caused it, but it happened. All the universe into basically a single point in space and time. It explodes outwards. For the first fractions of a second, we get through phases of physics where our current theories of physics don't work, where they break down. And we know they break down. There are some hypotheses, but they're not well tested. During this point, the universe also undergoes a burst of expansion that we call inflation, where it expands faster than the speed of light. So good to know that term. Inflation, expanding faster than the speed of light for a short amount of time. And then inflation slows down, the universe is still expanding and cooling, and then we begin to enter some subatomic regions where we can test what happens in our particle accelerators. About 100 seconds after the Big Bang, the universe begins nucleosynthesis, it begins nuclear fusion, and about 25% of the matter in the universe fuses from protons into helium, and a little bit of a few other elements, in particular deuterium and lithium. But nothing heavier than lithium. The universe doesn't have the right conditions for those to form. For the next 380,000 years, the universe is expanding and cooling, but not much is happening. Fusion has stopped. And at 380,000 years, the universe gets cool enough that the protons and electrons can combine, which allows light to stream freely through the universe, making the cosmic microwave background. And we can see that today. And the patterns that we see in there are fossil relics of proto-galaxies that are starting to form from clumps of dark matter and clumps of ordinary matter. But still, there are no normal stars. So we go through a couple 100 million years where there are no sources of light in the universe. Of course, the light from the cosmic microwave background is still there, but there are no stars. These are the dark ages. And then the first stars form somewhere around 250, 300 million years after the Big Bang. And from that point on, we can see light from what was happening. And from our vantage point at the Earth today, we can look back in time all the way almost to the start of these dark ages and observe how stars and galaxies have grown and changed ever since. So that's the takeaway point. If you can understand and tell a story similar to what I just did on this slide, you are doing very well. So that's it for our history of the universe. We've gone from the Big Bang up to today. In last unit, we went into the future, and so now you know everything that ever happened and ever will happen. Not too bad for 2 weeks worth of work, eh? In our third mini lecture, we'll talk about some of the evidence that shows that the story that I've just told you is indeed true.